Hello, we're going to start today with the first chapter of the book on fundamentals of electricity, and we're going to start at the website, and we're going to look at the information just for a minute on the website before we get started into the actual work in chapter 1. Now, here's our book. It's Fundamentals Text, chapters 1 through chapter 12, but up here there's also a book, and it is DC electrical circuit analysis, AC electrical circuit analysis, semiconductor devices, and then op amps. Okay, I'm just going to look at a minute at this book right here. Now, this is a 374-page book, and if we look in the table of contents of this book, we're going to see a lot of stuff, and we're actually missing some of this, and I just want to show it to you. Not that we're apologizing for it. It's just things that you might be interested in. If you're interested in reading the background of some of the things that we're going to be studying, you might have studied some of this in physics classes, or might have had it in another course someplace. But if you didn't, you might wonder some of these areas of what we're really talking about here. And these are not hard chapters to read through, but if you have a little bit of time, you might consider reading through them. So we're actually starting with chapter 3, but there's 2 chapters ahead of chapter 3, and the fundamentals is in chapter 1, and you might consider looking at specifically the scientific and engineering notation, significant digits and resolution. That might help you a little bit in some of these problems that we're working at. Chapter 2, we talk about basic quantities, and we're talking about the atomic model, charge and current. How do you get current from charge? Energy and voltage. So we talk about voltage, but it's behind it is concept of energy. And also we talk a little bit about power and efficiency. We talk about that later. And we also talk about resistance and conductance. We talk a lot about resistance and conductance, but basically this gives you the background information that you're going to use. So this chapter 3 starts with our chapter 1. So we're going to go back to our chapter, and we're going to look at our chapter 1, but it's really chapter 3 in most textbooks on electric circuits. So just want you to know that we're kind of skipping over some stuff, but that's okay. We're going to skip over a lot of stuff, but we just get the basics. Okay. So here in chapter 1, we call this electric circuits, and it's chapter 1 of the book, and in it we talk about flow, current flow, and a resistive load. And you can either have flow in the direction of from plus to minus, the plus up here and the minus down here, or you can have flow from minus to plus. Well, when we first were looking at this, and when people were first looking at this, they called it the flow of current was from plus to minus, when in fact the flow of electrons is really the opposite. And Ben Franklin was the person that did this, and he said the flow of electrons was plus to minus. And that's called conventional flow, even though it's opposite electron flow. Most texts use conventional flow. A few texts use electron flow. We're going to use conventional flow in this book. So, and if I define flow or current and that type of thing, we'll say conventional flow or from plus to minus. We go from the top to the bottom, plus to minus. Okay, so the relationship of voltage and current is this thing called resistance. You resist the flow. In other words, how do you stem the flow of current through a load? Well, you put a bigger resistor there. You put something that's going to hold it back more, and that's called resistance. Okay, so what could be a resistor? Well, anything could be basically that a light bulb, a resistor, a physical resistor, a motor, or a computer, anything plugged into a load can give you some resistance. So if the flow of electrons from negative to positive, we refer to the current flow from positive to negative. Okay, so this was a relationship that we give a value to called resistance, or R, and we define it as V over I, and we look at it and we say V equals IR, and you can take that to the bank. That's the equation that we use again and again and again in this course. Now you might be familiar with the equation Y equals mx plus b. That's the linear equation for a line, right? Any line you can define by Y equals mx plus b. That's from algebra days. Well, this is one of those equations where V equals IR, and as I varies, V varies. As V varies, I varies. But basically, what are we saying here? We're saying this is a graph that goes through the point 0, 0 because there is no B. B is 0. Okay, so I times R is M times X. Y is V, but there is no B, so B has to be 0. And that means we go through the point 0, 0. All right. So most of the time we do it the other way around. We vary V and we get the I, and that gives us the value of 1 over R. So the reciprocal of R, the 1 over R, is the value that we look at as for our slope in most graphs. So the M is really the 1 over R. We sometimes call that conductance or G, but in this book we just call it 1 over R. For the value of voltage and the value of current, find R. That's a classic problem. So for the value of voltage, 12, and for the value of current, 2, find R. And it's called 6. What is this over here? V over A. I don't know what V over A is. I know what ohms is. So V over A is defined as ohms, or the letter omega. So that's what we call V over A. It's ohms. The units of resistance is ohms, but it's really volts per amps. Now here is a graph of that V over the graph of I over V. Okay, so there it is. Y over X, I over V. So there it is. Now this is 1 over R. Don't forget that. This is the value of 1 over R. Is it linear? Yes, it is. What would you say about this graph over here? This is a graph of a device that we call a diode, and it is not linear. It's very non-linear, as a matter of fact. It's got a bend here, and it's got a bend here, and kind of linear up in here, and kind of linear in here, and kind of linear down here, but it doesn't, you couldn't draw a line through that anyway. So that's non-linear. So that's a device that is what we consider a non-linear device. So in this chapter, in this book, we're just going to consider linear devices, and we're not going to consider these over here until we get much later in the book. So basically that's the difference between a silicon device, this is a nonlinear device, and a device that's not got silicon in it. This is a linear device. So most of these devices over here are not silicon devices, or not semiconductor devices. Here's a classic semiconductor device. Okay, so here's linear, here's nonlinear, not a semiconductor. Okay. All right, so here we have the value of V, the value of I, find the value of R. So use the formula V equals IR, R equals V over I, 10 over 0.002, or 5,005K. Again, if you want to use that other text for additional problems, you can as you're working through these and say, I think I need a little bit more exercise on that. Well, there's your chance to go over to that other book and work some of these other problems. So I invite you to do that if you want to. Also, it's the change in y over the change in x. So that gives you the delta y, or what we call the slope. And that's 1 over r again. So let's get down here and work some of these problems. Now this is a homework assignment that I want you to try to do, and there'll be quiz questions out of this. I'm not going to ask you to hand this in, but I want you to try these, okay? So here in this first one, we have a V and we have an I, and we're going to ask for the R value. And I'm going to go over and we're going to get our table going here, and I'm going to get this set up and try to see what we got here. Okay, so we're going to look at it, and we're going to do a okay, so we're going to get the other, okay, just a second here, we'll get it going. Okay, so let's do this, transition over to it, and we're in business. Okay, so now we have the problem 1-1, which is a problem here. Okay, and for the load, find the resistance. So we have I is equal to 0.02 amps, and V is equal to 5 volts. So V equals IR V over I equals R. So 5 divided by 0.02, and that equals what? 5, get your calculator out. So R is equal to 250, right? What's the units? Ohms. Okay. So number 2, for the load, find the resistance. So I have a I of 3 microamps. Micro is what? 10 to the minus 6th, right? 10 to the minus 6th. And V is 12 volts. So again, R is equal to what? V over I, or 12 over 3 times 10 to the minus 6th. So what is R? Well, it's 12 divided by 3 is 4 times 10 to the 6th. Or 6, what is this? 4 mega ohms. Mega is 10 to the 6th. Okay, so let's do the next one. For a typical household voltage of 110, from 12 ohms flow, what is the load, the resistance? Well, you say, that's AC. Well, AC works the same as DC for something like this. So we have 110 volts. We have 12 amps. What is the resistance, or the load? Well, it's again 110. R equals V, 110 over 12. Okay, so we have 110 divided by 12. That equals 9.166, right? What is that? It's ohms. Okay, so let's keep on going. Number 4. For a DC electric motor with 90 volts and 7 amps, what is the load? 90 volts and 7 amps. What is R? 90 divided by 7, right? 90 divided by 7 is equal to what? 12.857 ohms. Okay. Then number 5, for the graph, find the current when the voltage is 4 or 8. Oh, so now I've got to figure out, this is a 2-step snake. Okay, everybody know what a 1-step snake is? Well, after it bites you, you only get to take 1 step before you die. Well, this is a 2-step snake, so you get 2 steps. Okay, so the first step is to find, in 1-5, is to find R. So you got a graph, right? You got a point on that graph. So you got 0.1 amp, and you have 2 volts. From that we can find R is 2 over 0.1, or 20. Now it asks us in 1.5, once we've got R, we can go hunting. So we can do this, find the voltage when the current, find the current when the voltage is 4. So now we use V equals IR, and we plug in for R, we plug in 20. And for V, we plug in 4. 4 equals I times 20, right? I is equal to 4 over 20, or what? 4 divided by 20, what? 0.2. And at 8 volts, okay, so now 8 is equal to I times 20. So here I is equal to 8 over 20, or 0.4 amps. Here we go in amps. Okay, so that's 1-5. Okay. Now, the next one is 1-6. Clean our page up here. Okay, so 1-6 is for the graph of current versus voltage in 1-3D. Find the current when the voltage is 15 volts. So we have this is again a 2-step snake, right? We have a value we're going to have to find R for. We've got a point here that we can get for 20 milliamps, we have 8 volts. R is equal to V 8 over 20 milliamps. Okay, 0.02 amps. So 8 divided by 0.02 is equal to what? 400, right? So that's 400 ohms. Now we can use that. It says find the current. I equals what when we have 8 or 15 volts. So now we can go back and we say V equals IR. V is 15. I times 400. Okay, so we plug this value in down here, and away we go. I is equal to 15 over 400. So these are good questions, right? These are good quiz questions. These are two-step problems, which is at least 0.0375. Okay, so that's 1-6. Okay, 1-7. For the graph of current of 1-C, find the voltage across the load when the current is 0.3 amps. Okay. So 1-C, we're going to go 1-3C. We've already found the current once, but let's just go back. Okay, find the voltage across the 1-3C. Let's go back to 1-3C, which is again resistance is 0.01 amp and 2 volts. R is V over I 0.1 or what? 20 ohms. So find the voltage when the current is 0.3 amps. So V is equal to I, or 0.3, times 20, or what? Or 6, right? So V equals 6 volts. What is the resistance of this load? We'll just go back up. There's our resistance right there. So we answered that question right there. Okay, moving on. For the graph of the current in figure 1-3D, find the voltage across the load when the current is 35 milliamps. Okay, so let's go back and do it again. They asked the question, we'll have to do it again. So here's our point, 20 milliamps, and 8 volts. So R is equal to V over I, or 0.02. 20 milliamps is 0.02 amps. So 8 divided by 0.02 is 400. So that's the number that we had before, so we're good to go. Okay. Now they want to know what V is. V equals 0.035, 35 milliamps times 400. So 400 times 0.035 is 14 volts. What are resistance? Right there's resistance. Okay, moving along. Some more. So for 1-4, okay, so 1-9, we're looking at the resistance of figure 1-4A. So in this one, what is the unknown? Well, we've got 2 volts. We have 4 microamps. What's the unknown? It's R. V over I, right? Is 2 over 4 times 10 to the minus 6th. So what is 2 divided by 4? 0.5, right? Times 10 to the 6th, or 0.5 or 500 K ohms. 500 times 10 to the 3rd K, or 10 to the 3rd ohms. So that's the answer to the number 9. Okay. 4-1B, what's the unknown? Find the voltage when the across the resistance of that one. So here we've got for 1-10, we have a resistor and we have a current. We have an I of 7 milliamps and we have a resistor of 5 K ohms. So this one wants to know V, right? V is what? IR. So it's 7 times 10 to the minus 3rd times 5 times 10 to the 3rd. This is one of those times when the milli and the K wipe each other out. So it's really 7 times 5, or 35. (1-11). Find the current across the load of figure 1-4C. And this one, what are we given? We're given the voltage, 15 plus 15 minus, we're given the volts, and we're given the resistance. R is 25 K ohms. Here we've given V equals unknown as I times resistance R, so V equals IR. So we use 15 is equal to I times 25 times 10 to the 3rd. I is equal to 15 over 25 times 10 to the 3rd. So it's 15 divided by 25, 0.6 times 10 to the minus 3rd, or equals 0.6 milliamps. That's number 11. Okay. After finding the resistance of 4-1A, calculate the current if the voltage is changed to 14. Okay, so now we go back to number 9, and I goofed because I forgot what that number was. So we're doing 1-12. We're moving ahead too quickly through these. Let's go back to 1-12. This is 1-4D. Here we have a summation of voltages. We have 2 milliamps. We start here, we go through one voltage, then we go through another voltage, and then we get to the bottom. So we have 2 milliamps flowing down here. And we have 5K, and we have 10K. Well, voltage is V times I, or 5 times 2 is 10. The K and the M cancel each other out. So this is 10 volts. And through 2 milliamps times 10K is 20 volts. Right? So what's the sum total here? We go through 10, and we go through 20, and we go through 30 volts. So we start up here, and we go down here, and we drop from 30 volts down to 0 volts. So we drop 30 volts. Okay. You don't have to worry about the word drop. We move through 30 volts. That's all we have to remember. 13. After finding the resistance of 1-4A, calculate the current of if the voltage is changed to 14 volts. So this is a little bit more involved. So we have to go back to to A. And if you remember, R is equal to V 2 over 4 microamps. So it's 0.5 times 10 to the 6th. So now we use that, and it says V equals, find the current if voltage is changed to 14. So I now have current is equal to V, right? 14 divided by what? So it's I is V over R, 0.5 times 10 to the 6th. So it's 14 divided by 0.5 equals 28 times 10 to the minus 6th. Okay. So we have 28 microamps. That's 13. For 14, if the current of 1-4B is 21 milliamps, what is the voltage? So I is 21 milliamps. So we changed it to that. So now instead of 7 milliamps, we go to 21 milliamps. What is the voltage? Okay, so in that case, we know the R. We just want to know the V. So we have the I, we have the R. Now I want to know the V, 21 milliamps times 5K ohms, excuse me. (21) times 5, 105, right? 105, and then the M cancels the K. 10 to the minus third, 10 to the third, they cancel each other out. So it's 21 times 5, or 105. And that's the answer. Number 15. If the voltage of 1-4C is 45, what is the new current? So this one, 1-C, if I change the voltage from 15 to 45, so the voltage here is 45, and I have 25 k ohms. What is the new current? I is equal to what? V over R. 25k, so it's 45 divided by 25 is equal to 1.8. And then 10 to the minus third. And that's the answer, okay? 1-16. If the current of 1-4D is changed to 5 milliamps, what is the new value of V1 and V2? So now I go through those two. I go through the first one, and I go through the second one. And what is the new value of V1? V1 is, it's 5K and 5 milliamps. So that's 25 volts. Down here I have 10K times 5 milliamps. That is 50 volts. What's the sum of the two? 75 volts. If 1 amp, number 17, if 1 amp equals 1 coulomb per second, and 1 coulomb is 6.24159 times 10 to the 19th electrons, find the number of electrons flowing in each of the circuits in 1-4 above. I'm going to let you do that one if you want to. I'm not going to ask you that one on a test, but that's something you might be interested in doing. For the diode of 1-2B, identify areas of high and low. Okay, so it does like this, right? It goes like this, and then it goes like this, and it goes like this. Okay, so this is I, this is V. So high resistance is right in through here for a little bit of current. This is high resistance. Big R. Up in here, little r. Down here, little r. Low resistance, high resistance in this range right in there. Okay. Okay. So now let's go back and let's look at what you're going to be thinking about in terms of your next lab. So we're going to go back now, and these are the problems. We're going to go back and we're going to look at the problems at the end of for the we're going to look at the labs. So let's go back and go back to the text. Okay, so we're going to go back. We're going to delete this one. Okay. So we're back in the text, and we're going to look at the rest of this chapter. So here we are, and this is our breadboard. So this is kind of looking at the lab and how a breadboard works. Here is a layout of a typical breadboard, and so the connectors that go down the sides usually go the whole length. So underneath, if you put a wire in any of these spots, they're connected. So the connections along the edges go all the way down. But across this way, you only connect these 5 together, and these 5 are connected underneath. These 5 are connected underneath. These 5, they're all connected underneath, but these 5. So if you want to make a wiring connection, typically what you would do would be to wire the plus to the one side, wire the minus to one of the sides on the other side, and then as you needed wires jumper out from that. Now this is an integrated chip, and you're not going to wire an integrated chip in this class, but if you were to wire an integrated chip, if you needed the power, you would just put a jumper over from there to one of these wires in this row, and see this last pin in this row connects to this chip, and that would give you the power. And this would give you your 0 volts down here. So that would give you the power and the 0 volts. And as you make connections, you would say, I'm going to put a resistor in here, and the resistor goes from here to here, and then that jumper's down to here. So you got a jumper from there to there. You got a jumper from here to here, and it goes all the way across to that pin. So basically, anything in this row is tied together. Now we also talk about resistances in this class, and the physical values of resistances are kept by this code. Black is 0, brown is 1, red is 2, etc., 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 all the way up. So you can just look at this, you can Google it, and you can figure out what the resistor value is by looking at these color codes, if you can see them. Most of the time you can, but with a lot of the resistors that we have, you can't see them. But if you could see them, this would give you the value. There's not a printed number, but it's based on the color codes. And this is how you would measure resistance. Okay, so you would use the VOM and set it to ohms, and then you would wire out from the one and put the one side of the resistor, and then the other side of the resistor go to the neutral. So out from the plus, in back at the minus, and that way you would actually set this up, I think right here, would set it on ohms, click it on this machine to ohms, and you would be able to use a clip lead to come out, tie it to the resistor, back from the clip lead to the neutral, and you're all set. And you give your reading, and that's how you do your labs. Okay? Now as you do various labs, you're going to learn that if you measure volts across, you measure volts across. You would measure voltage by using a pair of leads coming out of this one and this one, and you would go from one side and then the other with the 2 leads, and then you would click on DCV, DC volts. If you want to measure current, you have to open the circuit, and where you open the circuit, you would click on DCI or DC current, and then it would have to pass. You have to pass the meter would have to be on this lead and on this lead. So basically, you break the circuit in order to read current. You read across to read volts. You break the circuit to read amps or current. And there's your reading for current right there. Okay. So we're going to do this again and again. So use these 2 leads for the DCI, for the DC current, and they're labeled here on this side. You can't miss it, but basically top two leads on the right for voltage, middle and bottom for the current. So that's something to be prepared to do in your later labs. You don't do this in the first lab. In the first lab, you just do this. This is all you do. You measure a bunch of resistors and you report on them, and that's all you do for the first lab. Okay, take care and have a good day.